Hi, in this video we're going to be doing the Unit 7 problem set and the Unit 7 study guide, which is a review for everything we've done in Unit 7. Now to start off, what type of substance am I? It says black soft metals do not dissolve in water or benzene. The substance melts over a Bunsen burner to form a dull gray liquid that conducts electricity. When cooled, the resulting gray lump is still conductive. So now we know this element is conductive. What is conductive? Metals and metalloids. Now, how do we know if it's a metalloid? If it contains property of nonmetals. Does this contain property of nonmetals? It can. Not all nonmetals are soluble, and some nonmetals can be solid at room temperature as well. So this is most likely a metalloid, as it contains properties of both metals and nonmetals. Second question, it says this melts over a low Bunsen burner flame. Okay, so that means it has low melting point. It dissolves well in water, so dissolve well in water, which is most likely it's polar, and slightly in lighter fluid. It does not conduct electricity as a solid, and when a solution is tested, the solution doesn't conduct either. So not a good conductor. Do not conduct electricity. And now, what has a low melting point, is polar, and does not conduct electricity well? Well, then that is most likely a polar molecule. Polar molecules have a low melting point because all they have is dipole intermolecular forces. Polar molecules do not conduct electricity well. Next, rank for the following from the lowest relative melting point to highest. So it's telling us to, let's rephrase it. So it's telling us to weakest intermolecular forces to strongest, because weakest have low melting point. So let's see which one of these is weakest. This one we have CCOH 2, 3, 4, 5, H, and then 1, 2, 3, 4. All right. So this has dipole and H bonds. The strongest bond in this is H bond, because we have hydrogen connected to oxygens. Next, Cl2. We have this. Now this is completely nonpolar, so this is all this has is LDF. Now next, this is CaCl2. CaCl2. Now Ca is a cation and Cl is anions, so this is an ionic bond. This is ionic. And finally, we have CH3, Cl, and well, yeah, this is dipole because it's polar. Now let's see, we have one LDF, one H bond, one ionic, and one dipole. This makes it really easy because our weakest will be the LDF, second weakest will be dipole, which is D, third weakest will be H bonds, which is A, and finally our strongest one here is ionic bonds, which is C. This is from the weakest intermolecular force to strongest. Identify the substance in which hydrogen bonding can occur. So hydrogen can only bond to oxygen, nitrogen, and fluorine. So H bonded to N. So this can occur because H is bonding to an N. Now CaI2, there is not even hydrogen here, so definitely not. SiO2 doesn't have hydrogen either, so it wouldn't bond at all. Now CF4 doesn't have hydrogen in there as well, so it would not bond. So our only thing that could bond is NH3, which is H bonding to an N bond. A gas sample contains 0.1 moles of oxygen and 0.4 moles of nitrogen. If these sample is at standard temperature, what is the partial pressure of nitrogen? So partial pressure is the number of moles of what we're looking for, which is N2, divided by total number of moles, which is 0.5 if we add 0.4 and 0.1 together of total, and that is equal to 80%. So 1 times 1 atmosphere. So 1 atmosphere times 0.80 is 0.80 atmospheres. Now, if the temperature of the sample of an ideal gas confined in a 2.0 liter container. So let's do a P, V, T, N. Temp pressure, it goes from 1200 to X. Volume, it did not talk about volume, so we can ignore that. Temperature went from 27 plus 273, which is 27 plus 273 is 300, and 77 plus 273, which is 350. So it went from 300 to 350. Now, number of moles, it went from, it didn't tell us anything, so we don't need to worry about moles either. So we're only looking at temperature here. Now, temperature decreased. The relationship between temperature and pressure is inversely related. So as temperature decreases, pressure will increase. As temperature decreases, pressure increases. So we're going to use our 1200 times by a ratio bigger than 1, which means the 350 will go on top and the 300 will go on bottom. So now if we do that, we get 1200 times 350 times 2 divided by 300, which gives us 1400. And this will be mmHg, which is C. Number 8, when 4.0 moles of oxygen is confined in 24 liter, that's 176, the pressure is 6 atmosphere. Okay, so we have our PVTN chart again. Now, atmosphere is originally 6 atm, and we're looking for the new pressure, which is X atmospheres. Volume is 24 liters, and it did not change at all. Oh, no, it did. It went to 36 liters. So volume is 24 to 36. Temperature is 176 to 176, so temperature did not change at all. So we need to worry about temperature. Number of moles, 4.0 moles. 4.0 moles did not change either, so we can ignore number of moles. And that means we have volume, and we're comparing volume and temperature. And when volume increases, the pressure decreases. You have a container. Let's say you have a container with 4 moles of oxygen, right? As the volume increase, the pressure inside on these 4 will decrease, right? So volume increase equals temperature. Volume increase equals pressure decrease. So we're gonna have 6 times a ratio smaller than 1 to have a decreasing pressure, which is 24 over 36, which is 6 times 24 divided by 36. That gives us 4. So our new atmosphere is 4 atmosphere after we increase the volume. A gaseous mixture at a constant temperature contains O2, CO2, and He. Increasing average molecular speed. So molecular speed is the lightest one travels fastest. So let's write the speed for all 3 of these. We have O2, CO2, and He. O2 is 16 times 2, which is 32. CO2 is 32 plus C, which is 12.01. And that gives us 44.01. And He is 4.003. Now, the lightest travel the fastest, and the heaviest travel the slowest. So the order will be lightest, He, the second lightest, which is O2, and then the heaviest, CO2. And that one corresponds to D, He, O2, CO2. The lightest goes fastest, and the heaviest goes slowest. Finally, we have number 10. Hydrogen gas diffuses at a rate of 3 times faster than which of the following of the gases? So let's draw our little Graham's law. So our final answer, we want a number greater than 3. We want a number greater than 1 because we have a substance that travels 3 times faster. So the substance will go on the top and hydrogen will go on the bottom. Hydrogen gas is 2.02. And we put the X on top because we want a number that is equal to 3. Hydrogen travels 3 times faster than the gas. That means that gas will be heavier than hydrogen. And in order to get a number greater than 1, our heavier gas has to go on top. So now we square both sides. X divided by 2.02 is equal to 9. 9 times 2.02 gives us 18.18. So X is equal to 18.18. Now we solve which of these 18.18. This one is 32. N2 is 14 times, this is about 28-ish. He is 4. H2O is 18.002. Okay, so this is very close, and let's check CO2. CO2 is 32 plus 12, which is 44. It's 44.01. So our closest answer is D, H2O. And let's double check our work. Does this make sense? H2O, which is something that is significantly heavier than He, what does it make sense that He travels 3 times faster than a water molecule? And it does, because He is lighter. The volume of a simple gas measured at 30.0 degrees Celsius and 760 torr is 10 liters. So let's use a PVTN chart. This time we have temperature, which went from 30 degrees plus 273, which is 303 degrees Kelvin. And what is the final temperature? So our final is going to be X, which is what we're looking for. And gas volume went from 10 liters to 9 liters. And pressure did not change at all. So we don't need to worry about pressure, and we do not need to worry about the number of moles. This is the only two that we'll be looking at. So as pressure decreases, temperature also decreases. So we're going to use 303 and times multiplied by a number smaller than 1, which will be 9 over 10. The smaller one will go on top, and the bigger one will go on the bottom, to give us a number of 303 times 9 divided by 10 to get us a number of 227.7 degrees Kelvin. Now I want it in Celsius, so we're going to subtract 273 from that, and that gives us negative 0.3 degrees Celsius, and that is 0 degrees. Number 12, using this phase diagram. So for, it says the melting point of the solid. Melting point. This line is melting. Now, answer choice A says it decreases as pressure increases. As pressure increases, this indeed decreases. Let's say we have this pressure, right? The temperature over here will be about negative, let's say, negative 30. And if we increase the pressure, let's say we have here now, the new temperature will be here, which is even less than our previous one. So as melting point decreases as temperature increases, as pressure increases, which is correct. Let's check number 2. Negative 20 is at all pressure. So is negative 20 degrees the melting point of the solid is negative 20 degrees at all pressures. And that is not true, because it is only 10 atmospheres, or whatever this unit is, that is negative 20. So that's not true. Is 200 degrees C at all pressure. 200. This is not where the melting point is. Again, this line is melting. This line is melting. So 200 degrees is not even close to melting point. So that is wrong. Does not change with pressure. As you can see, as pressure changes, this line changes. So that is incorrect. And increases with increasing pressure. So as pressure increases, the melting point actually decreases with temperature. If this was true, then as pressure increases, our temperature will also have to increase, so the line will look at this. But since the line look like this, so as pressure increases, temperature actually decreases. So our answer choice is A. Now, if the solid is heated at 1 atmosphere, or so this is the atmosphere. Alright, if they're heated at 1 atmosphere, so we're going to be looking at this line, it will melt below negative 20 degrees Celsius. That is not true, because the melting point is all the way up here. So negative 20 degrees, it will not. So that's not true. Or sublime. Sublimation is turning from solid to gas. So at negative 20 degrees, does it turn from solid to gas? It does not, because sublimation line is over here, this one. That's wrong. Will melt at negative 20 degrees. Again, at negative 20 degrees, it does not melt, because the melting point is all the way up here. So that's wrong. Will sublime below negative 20 degrees, and that is true, because it sublimes all the way over here, which is obviously below negative 20 degrees. So our answer is D. Let's check the final answer, E. Negative 20 degrees will liquefy. And at negative 20 degrees, it is gas form. Because at this line, at this point, negative 20 degrees, it is within the gas form category. So our answer is D. Now, if the triple point now as for the triple point for number 14. The triple point is when all 3 substances exist in equilibrium, and it is that point over here. So what is the equilibrium point? 10 atmospheres and negative 20 degrees Celsius. 10 atmospheres and negative 20 degrees Celsius. Our answer is B. Everything else will be wrong. 15. A sample of gas is collected in a 500 milliliter bulb and at 22 degrees Celsius and is attached to a manometer. Okay, so the atmospheric pressure is 764 mmHg. This height is 55 mmHg. So it's asking for this. Now, which one has a stronger pressure? Because this one is taller, that means the gas inside is actually weaker than what's outside. And because it's weaker, we're going to minus 55 from 764. And that gives us an answer of, oh shoot, this is centimeters, mmHg. So first we're going to have to convert centimeters into millimeters. Well, 55 centimeters, 1 meter has 100 centimeters, and then 1,000 millimeters in every 1 meter. That would give us 55 cm is 550 millimeters. Now if we were to 764 minus 550 milliliters should give us 214 mmHg. Now we gotta convert into atmospheres. So for every 1 atmosphere, there's 760 mmHg. So we divide 214 by 760 mmHg, which gives us 0.282 atmospheres. And that is our final answer of B. And this one is supposed to be a lab, but we didn't do the lab in class, so we're going to skip this one. And number 17. The cooling curve to the right shows the temperature of a sample varies at time. Okay. At what time does the sample contain the most liquid? So this is solid, this line is solid, this line is liquid, this line is gas. So what line contains the most liquid? So T1 is over here, T2 is over here, T3 is over here, T4, and T5. So obviously at this point is where the most liquid is. So our answer is T4. The figure to the left shows that a solid hydrogen fluoride have two, what the following choices are accounts for two different distances. Alright, so why are there two different distances over here? Alright, cool. Accommodation of the necessary bond angles as a formation of solid. But first of all, this does not have anything to do with bonding angles, so that's A is wrong. Difference in strength between covalent and intermolecular attractions. That is true because H bond is what connects from hydrogen to fluorine, right? It's in between molecules. It's not within molecules. And what do you call the bond within molecules that bonds H and F together? Well, they're both nonmetals, so that is a covalent bond. This is a covalent bond, and this is an intermolecular bond, which explains why there is different distances. Different isotopes. We did not talk. There's not any isotopes in this, so that's wrong. Uneven repulsions among the non-bonding electron pairs. That is also wrong. So our answer is B. The graph to the right shows the temperature of a pure substance that is heated at a constant rate. As for the freezing point. So what is the freezing point of this? This is solid, liquid, and if there was one, this would be gas. So the freezing point will be this line. And this line is, no, the freezing point is when the process between this line, between liquid and solid. So this line will be the freezing point. And at what line does it start? Normal freezing at time T2. This will be the freezing point. This is the only line that is on the freezing point, which is this line. So the only line on this freezing point line will be T2B. Which of the following best describes what happens between T4 and T5? So what is going on in here? As you can see, there is no phase change. Try that again. What is going on between these two? Well, as you can see, there is no phase change, so it is not leaving liquid state. The solid and liquid phases, no, it does not exist in equilibrium. it'll be gas and liquid state. The solid and liquid phases, no, that's wrong. The vapor pressure is decreasing. The pressure is not decreasing at all. That's incorrect. The average intermolecular distance is increasing. And that is what this line is all about, right? These lines, as energy increases, the phase does not change because these energy are used to break down the intermolecular forces. And when the intermolecular is broke down, the distance in between is increasing. And so the average intermolecular difference is decreased. So that's D. Now, the temperature of the substance is increasing. That is wrong because, as we can see, this is temperature and this is a straight line that does not change. The phase diagram of the pure element X is shown to the right. The temperature of the sample is raised from this to this. What is the expected behavior of the substance? So we're looking at 0.5 atm. Expected to turn into liquid at 70. That is not true. That's solid, liquid, gas. That is not true. Again, we'll be only looking at this line. It melts at about 30 degrees. It does not. 30 degrees over here, but the pressure is incorrect. So A and B are wrong. It melts at about 20 degrees. That is correct. And remains liquid until it is greater than 100. No, actually no. That is the first part that I'm correct because this is a sublimation line. So that's correct. That's incorrect. It sublimes to a vapor pressure at 20 degrees. Yes, that is what we're looking for. This line is sublimation and deposition. So yes, it does sublime at 20 degrees Celsius. It remains a solid until the temperature is greater than 100. No, by the time it's 100, it's already long being a gas. So our answer is D. Now this substance at negative 40 degrees, which is over here, and 1 atmosphere, which is over here, would be liquid or solid gas. Again, this is solid, this is liquid, this is gas. So it will be a gas. Now at negative 40 degrees, carbon dioxide is compressed from 1 atmosphere to 7 atmosphere. So you have 1 atmosphere all the way up to 7. No. All the way up to 7. And the temperature remains same. So now we're looking at this point. Now it can conclude that H2 will condense into a liquid because now it is in the liquid form. So our answer is A. And it does not condense into solid, it does not vaporize into a gas, it does not melt, and does not sublime. So it's A. How many moles are in a gas sample occupying? Alright, so now we've got to use our PV equals nRT formula. And first let's convert torr into mmHg. And I know you can do this in your head because 1 torr is equal to 1 mmHg, but it's best if you show your work. And we have 760 mmHg for every 760 torr. So this does not change at all, which means it's 170. Whoops. So this is 0, my bad. Torr. No, mmHg. Ooh, making a lot of mistakes. Torr over here and mmHg over here. Correct. There we go. Now, that is pressure times our volume, which is 0.5, equals N, and we're using mmHg, and the gas constant for that is 62.4 times temperature, 25 degrees Celsius. We're going to use Kelvin, so 25 plus 273, which is 298. And we need to multiply that by the number of moles, N, right? So 170 divided by 2, which is 85. 85 is equal to 62.4 times 298. 18595.2 N. Divide both sides by that. 85 divided by this. We get the number of moles as 0.00457, which is about B. Number 5, it's same thing. PV equal nRT. Now it gave us mmHg. Everything looks right. So we have pressure, which is 821, times volume. V is 1 liter, is equal to number of moles, which we do not know, N. It's asking for the number of moles, times constant, which is the same constant as before, as they're both in mmHg, which is 62.4, and times temperature, which is 56 plus 273, 329 Kelvin. And we'll do that is equal to 821 is equal to 62.4 times 329, 20529.6 x. We divide both sides by that number. 821 divided by 20529.6 gives us 0.03999 molecules. Oh no, this is moles, number of moles, and then we gotta convert it to molecules. Oopsie, so we have moles, and then we convert it to molecules. So for every 1 mole, there's an Avogadro's number of molecules, if you recall back, times 10 to the 23rd. So we're gonna do 0.3999 times Avogadro's number, which is 6.022 e to the 23rd, and that is 2.408 times 10 to the negative 22. 2.408 times 10 to the negative 22, which is about E, 2.41 times 10 to the 10 times 10 to the 22nd. An unknown gas X has a rate of fusion measured to be 1.14 times of that of carbon dioxide. So we have carbon dioxide, which is CO2, and CO2 is equal to 44.01. So it's going to be faster than 44.01. So it's going to be obviously lighter than CO2. So let's do this and put a heavier one on top. 44.01, lighter one on bottom, because our rate of speed is higher than 1, which is equal to 1.14. Square both sides. 1.14 squared is equal to 40. And I'm going to do 2 steps in my head. So I'm going to multiply that by x as well. So we have 44.01 is equal to 1.14 squared, which is 1.2996x. Now divide both sides by that, which is 44.01 divided by 1.2996. That gives us 33.86. So which of these gases have 33.06? Well, first, let's do oxygen times 2, 32. C2, which is 12.01 times 2 plus 1.01 times 6, 30.26. Next, we have CO, which is 12.01 plus 16, which is 28.01. Next, I have pH3. P is 30.97 plus 1.01 times 3, which is 34. Okay, that is very close to 33.86. Now let's check N. N is 14.01 plus 16 times 2, which is 46. 46.1. So our final answer will be D. With a molecular weight of 33.86, and that will be 1.14 times faster than how fast CO2 will travel. 27, that is the same kind of problem. We have, oh wait, no, this was PV equal nRT, sorry. PV equals nRT. Let's convert torr 750 torr into mmHg first, which is still 750 mmHg. Now I have 750 mmHg times liters, 0.2 liters equals, we're looking for the number of moles, which is N, times pressure, times R, which is 62.4 again, since we're using mmHg, times temperature, which is negative 73 plus 273, which is positive 200. And now we multiply all that together. 750 times 0.2 gives us, 750 times 0.2 gives us 150. Equals 62.4 times 200, which is 12480x. Divide both sides by that. 150 divided by that gives us 0.0120. That's number of moles, right? Now for number of moles, we have that much gases, that much grams. So moles of X is equal to 0.385 grams. And now we divide both sides. 0.385 divided by 0.10120. That gives us x is equal to 32.08. Because the number of moles of this substance is equal to the number of grams if they're in the same, if we're talking about the same reaction, right? So we have 32.08, and what substance is 32.08? Oh, we don't need to do that. We already have 30.08, which is C. #28, we have a gas given that much pressure, liters, temperature. So PV equals nRT. No, PVTN. So we have 5 liters of volume, 62 torrs as pressure, 27 degrees plus 273, which gives 300 degrees, and we do not look at N, which volume will be the same of the mass as 375. So pressure increased a lot, and temperature also increased. 177 plus 273 is 450 Kelvin. So what is going on with V? Now first, let's take a look at temperature and volume only. Temperature and volume are directly proportional. So 5 times as temperature increases, volume will increase as well. So this time 450 will go on the top, 300 will go on the bottom. Now we ignore T and only look at P and V. Pressure and volume are inversely proportional. So as pressure increase, volume would actually decrease. So this time the 62 will go on top. 62.5 divided by 375 to get a number less than 1. Now we have 5 times 450 times 62.5 divided by 300 divided by 375 gives us the answer of 1.25, and the units will be in liters. Next one, we have this much temperature, this much pressure. This will be PV equals nRT. All right, pressure is 335 kPa, so we're gonna have to convert kPa. No, actually no, we do not need to convert. kPa is one of them. 335 times the liters, which is 1, is equal to number of moles, which is X, times the gas unit, which is, oh wait, no, number of moles is, we do know that. We have 5.68 grams of O2, right? So 1 mole of O2 will contain 32. So it's 5.68 divided by 32, which gives us 0.1775 moles of O2 times that gas constant, which is 8.314, times, what are we missing? Temperature, T. So we have 335 is equal to 0.1775 times 8.314, which is equal to 1.4757 x, or T. And we do 335 divided by that gives an x of 227 Kelvin. Now to convert from Kelvin to temperature, we're going to subtract 273 from it. That gives us, this is degrees Celsius. And we subtract 273, that gives us x is equal to negative 46 degrees K. So B. And finally, number 30, a mixture of 2.00 grams of nitrogen gas. So 2.00 grams of nitrogen gas. And that much grams. The mixture is equilibrium at that much. What is the partial pressure, right? So first let's convert everything to moles. And that will be 2 divided by 28.02 will be 0.07, 137.759. And on the other hand, we have SO3, 3.25 grams of SO3, 1 mole. SO is 16 times 3 plus S, which is 32.07. That gives us 80.07. And this number gives us 3.25 divided by that. That gives us 0.040589. So now I'm going to have to add the two together. So we're looking for atmosphere. So we're going to use PV equal nRT formula. And pressure we do not know. We're going to use volume, which is 4 liters. 4 times P is equal to number of moles, which is these two added together, right? 0.07137759 plus 0.040589, which gives us 0.111, nope. Alright, it gives us 0.1196659. So about that, yeah, okay. Times, this time we're using atmosphere, so the gas constant for atmosphere is 0.0821 times temperature in Kelvin, which is 75 plus 273, 348 Kelvin. Now we do all of that. We have, again, if you're wondering where I got this number from, we're going to use total pressure of these two to get it. And to get the total number of moles, and then we're going to use that to solve for partial pressure. So now, what does the pressure give us? 4P is equal to 0.111966659 times 0.0821 times 348 gives us 3.198975. Divided by 4, we have 0.77. Here, this number is the pressure of the whole vessel. And first we're going to use pressure of nitrogen divided by the total pressure of the two gases, which will be 0.07137759 plus 0.040589, and then multiply that by our and then multiply by our P over here, 0.7997. Because this is how the law works, right? You're going to use the pressure we're looking for divided by the total pressure and multiply it by the pressure of the container. So where are we? 0.07137759 divided by a total, which is 0.111966659, and multiply by 0.7997. That gives us an answer of 0.5098, which is 0.1, and the answer is not D. In the Dalton's law of partial pressure, it is pressure of what you're looking for, in this case N2, divided by the total amount of pressure, which is N2 plus SO3, which gives us 0.1196259, and then we multiply it depending on the grams, liters, and temperature to get our final answer of the partial pressure. Which of the following substances have the lowest boiling point? So this is temperature, and these are temperature, and which of them boils the earliest at, let's say, 100 pressure, 100 vapor pressure, right? Standard vapor pressure. So which of the following substances have the lowest normal boiling point? So normal is standard boiling pressure. So which of these have the lowest temperature? Well, that is propane. And at what temperature will ethanol boil when the temperature is 50 kPa? When the atomic pressure is 50 kPa. So this is 50 kPa and ethanol. Alright, this is ethanol. So when it's at 50, how hot does it get into ethanol boils? So about 70 degrees Celsius. Nope, my bad. Sorry, this is not 70. This is 62. About 62 degrees Celsius. At what atomic pressure will water boil at 90 degrees? Water, this line is water. 90 degrees is 75. This is 90 degrees. So about 70 kPa. Of which of the substances have the lowest vapor pressure at 70 degrees Celsius? So when we're at 70 degrees Celsius, Which of these has the lowest vapor pressure? Well, that is this point, right? This point is ethanolic acid. Which of the following has strongest IMF? So the stronger the IMF, the higher the boiling point. So as you can see, this one has the highest boiling point. So the same as above. Ethanoic acid. Now, which of the following is most volatile? So volatile is low boiling point. Right here. Let's do G first. Volatile is low boiling point, low vapor pressure, and weak intermolecular force. So which of them have the weakest intermolecular forces and lowest boiling point? Well, that is the same answer to our number 1, which is propane. Now, a metallic cylinder with volume of 5.25 liters contains this much of this. Calculate the total pressure. So, we first got to convert everything into moles, right? We have 3.22 grams of He. 1 mole of He is 4.003, and that equals 0.8044. Next, we have 11.56 grams of N2, sorry. And 1 mole of N2 is 28.02. 11.56 divided by 28.02 gives us 0.41. 41256. Now, okay, that's it. So we have PV equals nRT. We need the pressure. P is pressure, volume is 5.25. P is equal to N, number of moles, which is this plus this, 0.8444, 0.8044 plus 0.41256 gives us 1.21696. And let's use atmospheres, since it didn't ask us which one to use. So 0.0821 is the gas molecule for atmospheres, and we multiply by the temperature, which is 15 plus 273, which is 288 Kelvin. And 1.21696 times 228 times 0.0821 gives us 5.25 P is equal to 28.774 divided by 5.25, and that gives us an answer of pressure is equal to 5.48 atmospheres. Calculate the partial pressure for N2 in a cylinder. Okay, so that is moles of N2, which is 0.41256 divided by total moles, which is 1.21696 multiplied by total pressure, which is 5.48. And that gives us 0.41256 divided by 1.21696 times 5.48. That should give us about 1.86 atmospheres. 33. For the following reaction took place. Okay, what is the partial pressure of oxygen? So we have partial pressure of oxygen is equal to the pressure of KClO3 minus the pressure of KCl, which is equal to, let's see. So our reaction is oxygen gas over water, and we're going to use what we have, which is 755 total minus the water to get the partial pressure of the oxygen. So the water is 30, and that gives us 755 minus 30, that gives us 725 mmHg. What is the dry volume of oxygen gas? Alright, so let's do PVTN. We're looking for volume, and our original pressure of the oxygen that we found in the previous problem is 725. Then it became 760. And our volume is 1.45 liters. And then X is the volume we're looking for. Temperature went from 29 degrees, which is 29 plus 273, 302 degrees Kelvin became 273 degrees Kelvin, and we will not use N in this one. So let's do volume and pressure first. They are inversely related. So we're going to do 1.45, and as pressure increase, volume decrease. So we're going to put the smaller number on top, which is 725 divided by 760. And then volume and temperature also are directly proportional. So as temperature decreases, volume will also decrease. So this one we're going to use put the smaller one on top as well. And that gives us 1.45 times 273 times 725 divided by 302 divided by 760, which gives an answer of 1.25 liters. See how many moles of oxygen is used. So now let's use a PV equals nRT formula, where pressure is 760 because it turned into 760 times liter, which is 1.25 as we just found over here. Now that equals X amount of moles times, let's see, we're using mmHg, right? mmHg is 62.4 gas constant, times, we're going to multiply that by 273 Kelvin, and that's from here. So 760 times 1.25, that gives us 950 is equal to 62.4 times 273 is equal to 17035.2 N. Now 950 divided by that number, that gives us N is equal to 0.0558 moles of oxygen. Now, what is the mass of KClO that was consumed? To find the mass of this, we're going to use what we have already, 0.0558 moles of O2. And then for every 2 moles of O2, sorry. As we can see up here, for every 3 moles of O2, there's 2 moles of KClO. So 3 moles of O2 and 2 moles of KClO3. So we're going to do 0.0558 divided by 3 times 2. That gives us 0.0372 moles of KClO3. And then we're going to use 1 mole of KClO3 and find the weight of that. 1 mole of K is 39.1 plus Cl, which is 35.45, plus 16 times 3, which gives us 122.55, and we do multiply that by 0.0372, and that gives us an answer of 4.56 grams of KClO3. Number 34, equal molar quantities of two gases, O2 and H2, are confined in a closed vessel at constant temperature. What gas, if any, has greater partial pressure? Alright, both are the same. Both gases have the same partial pressure because equal moles means equal pressure in the same conditions. Which gas, if any, has higher density? They both have same volume and moles, but oxygen has a larger mass, so oxygen is more dense. Which gas, if any, has greater concentration? Concentration is moles divided by liters. For both of them, liters and moles are the same. As I said in the beginning, there's equal molar quantities in a closed vessel. So liters and moles are the same. So density will be same. So concentration will be same too. Which gas, if any, has greater average kinetic energy? Now this one we learned that kinetic energy is directly related to temperature. Temperature did not change, so they have the same kinetic energy. Which gas, if any, will show greater deviation from ideal behavior? So oxygen has LDF, water has LDF, dipole, talk about the intermolecular forces over here, and H bonds. Stronger IMF equals stronger deviation. So water will deviate more from ideal behavior due to its H bond. Which gas, if any, has higher average molecular speed? And we learned that H2O. Why? Because according to Graham's law, when constant temperature, lighter molecules move faster. H2O is lighter than O2, which is why it will move faster. Which is why, let's say, it will have a greater average molecular speed. Now, we need to draw a complete Lewis dot structure. Alright, so first we got to, for part A, we need to complete this Lewis dot structure, which is 20 valence electrons. And over here right now, we have 16, 17, 18, 19, 20, and everything fills our tetrahedral, so great. Now, in the box Y, draw a complete Lewis dot structure for the other one. So we'll have to draw a different form. And this time, let's see, we can have C in the center. We can draw something like this. H, 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 H. And this way, we're going to have 2 in the middle as well. There we go. So both of these are the exact same elements, but they look differently. So based on the Lewis dot structures you drew in part A and the formation data above, justify compound 1 or 2 that is base representing box X. So is this compound 1 or compound 2? They both have the same formula, but their boiling points are different. So here's our explanation, part B. Box Y is compound 1. Compound 1, which is this one, because it has a lower boiling point. This is due to weaker bonds. Box X has a hydrogen bond, since H is bonded to O, but that doesn't exist in box Y. The strongest bond in box Y is dipole, since the dipoles do not cancel, and therefore makes it a polar compound. And with the H bond in box X, that means box X has a stronger intermolecular force. A stronger intermolecular force means a higher boiling point, and therefore box X is element 2, the one with the higher boiling point. So let's look over here, right? Negative 24 degrees for boiling point and 78 degrees for boiling point. Compound 2 is obviously higher. Now if you look over here, we have H bonded to an O, so this has an H bond. But the strongest bond in here is a dipole bond because it's a polar molecule. Dipole. So now that we're comparing H bond to dipole, H bond is a lot stronger than that of dipole. So that means this one will have a lower boiling point as its intermolecular forces are weaker. And this one will have a higher boiling point since its intermolecular force is stronger. And since this one has a higher boiling point, we know that box X is equal to compound 2. And box Y is equal to compound 1. Thank you for watching.